Hi, my name is João. I'm one of the PhD students here in the Wireless Intelligence Lab, and in this video, I'm going to show you how to reproduce the results of localization in Digital Twin MIMO Networks, a case for massive fingerprinting. We just got it accepted in a workshop in ICC, and the results we're going to reproduce in this video are, I'm going to show you how to do this image, that figure, and these two figures. And this table will come as a result of those two figures. And I'll show you essentially how to reproduce all of this. Just before diving into the results, let me first guide you through this page and tell you where you can find what, and provide you a short introduction of what we try to do in this paper, because there's still going to be a few months until the ICC presentation, and I think a video about the code should be, you should understand what we try to do. So you already know you can find the paper here, the code will be here, and this repository is public and it's marked on the paper. Yep, it's this repository here. And this video will be the video of the presentation once we make it. And this should be halfway through the summer. I think it's June 6th for ICC 2024. I might as well check that. June, yeah, well, 14, either 13th or 9th, which is the workshops. It should be available at that point. In the dataset, we use DeepMIMO. And if you click here, you get to the DeepMIMO page and you can test different versions in different scenarios. We're about to release v3, but currently we still use v2 in this code. In this case, you don't have to download any DeepMIMO scenarios because we include the scenario here, and everything is already linked, so you only need to download the code. Before we go in there, let me introduce you what we try to do. And there is a nice image that shows our idea, essentially. And this is an image about fingerprinting, because fingerprinting is one of the most scalable localization approaches. But that localization approach has been bottlenecked in some way because it is so hard to create databases for fingerprinting. For example, just to provide some idea of why fingerprinting is so scalable, it doesn't require any hardware compared with the multipath based approaches, which require very precise multipath resolution hardware and sounding hardware, or with the time of arrival approaches. Those require very tight synchronization and sometimes specific hardware to do that as well. And then even besides the time of arrival and the multipath approaches, you also have the angular approaches, which require a lot of antennas to get a proper angle resolution. And many of these methods, beyond this, they still require multiple base stations. And sometimes many of them don't work in line of sight. So fingerprinting solves many of these issues. Although it has other issues as well, which we're gonna see in the journal of this. In a month or two, it should be out. And essentially, what this image tries to show is the correlation of the database to a location. If the database is small, there might be not that much correlation. If we only have one received power, there are many places where the user can receive a certain amount of power. Now, if we increase the database and now we have two received powers from the power measured from two access points, for example, or the power measurement in two different bands, or the power measurement in two different beams. Essentially, this will narrow down the number or the amount of possible localizations where the user can be and perform this measurement. And the more information we collect about the user, the less likely it is that the smaller is the subset of positions where it can be and perform those measurements. Of course, there's noise included. So essentially, the larger the database, the more accurate we can get the localization, because we get a higher bijectiveness between the database and the locations. So this essentially summarizes why we try to increase rather than decrease our database. And this is a fundamental of fingerprinting. Now, the problem is increasing a database is very hard for fingerprinting because it requires going outside and performing measurements, especially if you want a large database. You have to perform measurements in different beams, bands, with different base stations. So it's hard and it takes a long time and a lot of human effort. That's why using digital twins seemed such a good solution, because we can essentially virtually eliminate, but let's be conservative and say drastically reduce the effort required to make these very large databases. And essentially we are transforming the problem of localization into the problem of realistic digital twins. So while the problem of creating databases was very hard and there were no very good solutions, now we have the problem of creating a realistic digital twin, which everybody's trying to solve anyway. So by transforming this problem, we got quite a different problem to work with. And in this paper we show that using that digital twin, we can have indeed databases that are large enough to get a really good accuracy despite noises that occur from using the phone, because there's fading caused by people moving, right? Okay, so that's the introduction, and here we just make a diagram of how the user will perform the measurement. In this case, there will be downlink signals, and the user makes the measurement, measures the received signal strength, which is just a power, in many beams, in many bands, possibly consecutive times, and then it reports that to the base station, and the base station can use this to triangulate the user. For example, measures across different time in the same band and beam can perhaps be averaged out, and that way suppose it's a normal distribution, we can collect several points there and find the mean, and the mean is the most common value that the user would report, assuming a normal distribution. And in this paper we assume that. So this is the gist, the short. This is a short introduction of the paper. Now let's dive into the results. To reproduce the paper, what you can do is, one last thing that is relevant to understand is how we created the databases, because the code is essentially going to create these databases, and it's really worthwhile understanding what the code is doing. So let me zoom in a bit here. Let me see if I have a better resolution of this image to show you. I do. Great. So let us assume this is just an example. We have Boston here, and we created the digital twin of the Boston. In this case, this already exists. It's Boston 5G. You can find it in the DeepMIMO page, but this is not a scenario we used. We used a simple proof of concept. Based on this 3D model of the city of Boston, we computed ray tracing, and this ray tracing, we then created the DeepMIMO scenario out of it. And this DeepMIMO allows us to use antennas of different sizes, compute the channels for different bands, and that's what we use to create these digital twin RF maps. Each map is essentially the received power in each position for a given band and for a given beam. So in this case, let's assume this is band 0, which might be exactly at 3.5 GHz, and then band 1 might be 10 MHz later. higher. And here we see different beams. This is, for example, beam 1, beam 2, beam 10. We're going to see exactly which beam is which. But essentially, after computing the received power in each position for each beam, then we know what the user is supposed to report in that position when we are using a certain beam. So this will allow us to triangulate the user when it tells us that it received a certain power in a certain beam. So essentially, after some reports measured in a certain position for a certain beam, band, and time, we will compute the likelihoods of the user being in certain positions given the measurement and given our database. And we essentially compact or we merge all those into a final probability grid, and then we essentially use the maximum likelihood or the position that has the maximum probability of the user being in that place, assuming in our case the normal distributions. We report that position back. We have to make some sort of assumption about our distributions, but it should be known that during operation we can adjust our estimation of the distributions. They don't need to be always normal, and as we get real world data, we can adjust those distribution beliefs. Okay, I think this provided a good intuition of what we're trying to do, and to reproduce the results you can go to this repository, which you can find here in the code, and you can download. Yep, let's download directly. Can I open this? Yep, here we are. We can extract it, and I'm going to open the terminal here. And according to this README page, it tells you here what you need to do to set up a Python environment to run this code. And in this case, I'm going to follow these exact steps to set up the environment. First, you need to install Miniforge. And you go to Miniforge, and if you are in Windows, you download here. Mac OS, Linux, these ones might be only scripts that you need to run, but essentially after running them, you will need to open the Miniforge prompt in Windows, which after installing, it should appear in your start menu, and in Linux and Mac, you just open the terminal. So since I'm in Linux, I'm just going to open the terminal, but this is exactly the same thing as you would do in Mac and in Windows in the Miniforge prompt. So now you just have to type these commands, and I'm going to paste them, and I'm going to accept all of them, and I'm going to speed up this part for you to see, but essentially I'll meet you at the end. Okay, it was fast, it was done, it's done. Note that in one of the commands I installed spider kernels, and if you are using another IDE, you don't need to install the spider kernels. I did because I like to use spider, and you can install spider here. So let us open spider. Yep, here we are, and let us navigate to the right interpreter, which right now it's already enabled. Yep, with the right version Python, although it works for practically all the versions. And then downloads Digital Twin Main, which is where we are here. Great. And our scenario is here in DeepMIMO Scenarios. It's this new scenario. And I included, these files are the DeepMIMO files, and I included the Blender file, which I have opened here. In this case, it's coming from another directory, but it's the same file. and this is what you'll see in the Blender file. And this is our scenario. From the top, we put a base station here, pointing at minus 45 degrees, so you can imagine 0 degrees pointing to plus X, and then 45 sort of in this direction. This is where our base station is going to be. And we scatter the user grid in this scenario, and we're going to visualize that user grid. This is a very proof of concept scenario, just as an example. Okay, so we can remove this from here, and this part is done already. And now this is the code. Okay, this is from GitHub actually, but we can, okay, this one is the right one. It's the same file. So here we are in the code, and I'm essentially going to run each cell and explain as things run. So if I click here, Shift Enter, it runs a cell and it skips to the next one. And while this generates the channels, I'm going to explain some parameters here. And I'm going to tell you the flow. So this is the frequency of our simulation, the position of the base station, and you can sort of understand this position. If I pull this here, this is the scenario again, and the 0 is there, and the axis is to the right, and the y is up, up on this green line. You can see the axis here. So if we put minus 42, it's essentially going to be this side. This is centered at minus 55, and it has size 30. So this edge here is going to be minus 40 x, and so the base station is going to be 2 meters inside or to the left of this one, and essentially for the y is more or less the same. It's at 40, so minus 15 would be 25, and plus 2 would be 27. So the base station is essentially 2 meters. It's more or less here, let's say, and also 2 meters height, and it's 30 meters. Yeah. So the base station is more or less here, and it's pointing at 45-degree direction, which we point here. This direction is around the z-axis, so you can imagine the z up, and plus will be to rotate towards the y direction, and we rotate minus 45 in the opposite direction. That's why we have, instead of rotating to that direction, we rotate minus 45 here. So the base station. The bandwidth 100 megahertz. It's a band of 5, so we have 20 in total. We have a field of view of 120 degrees, and this goes between minus 60 and plus 60. So we spread 25 beams between these angles, which results in a beam resolution of 5. And we have a 64 antennas on the horizontal axis and one on the vertical, so it's essentially a ULA. This is the number of decimals that we use in the received power resolution. The cell size, which this will tell us the distance between users, we only use it to make the simulation faster, essentially. Now, yeah, and these are some parameters to fetch the scenario, because our scenario here is called new scenario, a default name, and the scenarios folder needs to be DeepMIMO. These are all parameters that are used by DeepMIMO, as DeepMIMO usually uses parameters. Yeah, and the save folder, because we are going to save the database to this folder. Yeah. And so throughout DeepMIMO, we copy the parameters from the defaults, we change the ones we are interested in. In this case, this scenario has 140 positions across Y. So let me put this like this. So this, if you see the size of this, it's 200 by 160, and if you take 10 meters of each side, it's going to be 180 by 140, and we placed one user per meter across each axis. So if we do here 181, because we started on 180 on minus 90 and we went to plus 90, including the 0, yeah. So if we do this times 141, we got this number, and this is the number of users we generated here. But then we filter down the channel to user spaced every other user, essentially. So that's how we got, if we do here 91, if we do here 71, we got 6,000, and then we filter down further based on the users that are inside the buildings. And essentially, if we check here the number of active users, it's this number, and because there are users that are inside the buildings, and it's those we don't see. So essentially, this code generates the data set in generate, which is, where is okay, generate is here. We generate the data set here, and this part of the code handles the codebook for creating the beams in those directions. The directions are these ones that we talked about before. These are 25 beams. And then this part of the code essentially will take care of the subsampling of these positions by picking every other user, and this fixes a little generation error, and here we essentially apply the beams to the channels. And so this is really where we create our database. This is the beginning of our database, which is number of beams, it's 25, by number of bands, which is 20, by the number of active users. So this will be the size of our database, and we can, for example, this is the number of values that are in our database, just over 2 million 1 decimal points. Just so you see, these are our RSS values in dBm. And so we run this to create our database, which is a structure that is going to help us make some computations. So now, something really worthwhile showing is how the database looks like. Essentially, how the coverage looks like for each beam. And this is a fairly low resolution visualization, because I am using 2 by 2, but if you do it 1 by 1, it's going to be a much better visualization. Essentially, you see here the coverage of each coverage in each position from using a certain beam, and this is for a certain band. So if a user measures, for example, minus 60, then we can tell most likely the user is here along this beam. If the user measures minus 60 in beam 6. And we can do the same for the band. And you see it changes much less, but it still oscillates. Yeah, it still oscillates, and it still provides helpful information. Now, if we want to check what beam is the best for in each position, we see a progression in the line of sight part. We see the natural progression of beam 0 more to the left, and then we progress to the positive beams and beam 25 here on the right. We can also plot, just to understand better, what it looks like when the user receives the maximum power in each location. What is the maximum power possible by using the optimum beam? And I just let this here for you to understand and to explore. Now, let us. I also did some testing essentially to make sure that my generator was working well. So in this case, I tried to generate samples in a certain beam. I tried to generate samples in a certain beam and a certain band and some time instance, and that's what we're going to see here. So for beam 3 and band 3, the average value is -88 dBm, and we generated many values, essentially sampling from a normal distribution with a mean in that place. And essentially, when I say perform a measurement, I mean sampling one point from this distribution. And obviously, the width of the distribution matters a lot for how easy it's going to be to localize the user. For example, if I change here the standard deviation to 1, you can see here that this is, so to remind you, 99% of the points are between 3 standard deviations in normal distributions. So essentially, if I change this to 1, we should have a shrinkage to more or less 87. And let me indeed do that. Yeah, that's what we see here. We saw a larger shrinkage, and this essentially just resamples many times the distributions and displays them. Essentially, this parameter is going to be very important for the accuracy we are able to get, and we saw a few papers that considered that if the user is more or less static, it should not oscillate much beyond plus or minus 5 dB. And by using 2, we are considering that 99% of the points are going to be between plus and minus 6. So it's a relatively decent approximation, but in the journal that we are about to publish, we test how performance varies with this parameter, which is very important. So some more testing, just to make sure everything is working. We tested reports in a given beam. So by telling the user, give me reports in this beam, in this band, and 5 of them, we try to localize the user. Yeah, and as you can tell, the localization is not great. In this case, we tried to localize the user in this position, the pink one, and we got the blue one. Yeah, we tried the ground truth was this one, and we got another one. And these are the 3 most likely positions. And this is because maybe beam 12 is not received with a lot of power, and so there are some random probability clouds essentially. So these first 5 are the 5 measurements that are performed in a given beam, and we got -99, -98, etc. And then the probability grid that is merged from those measurements, and where are the 3 most likely positions, and then we get the maximum position there, resulting in an error of almost 5 meters. Now what we do in the paper is not telling a certain beam. We say perform the measurements in the beams you receive the best, and here we change that to NK, and in this case this was also very low standard deviation, so now we are using a more normal one. But by performing measurements in a certain beam NK, in a certain 3 beams NK, just one measurement, we usually get better results. Exactly. So let me okay, yeah, it stopped. This is the first plot we're gonna look at. So the first beam is this one. It's not very clear that it is a beam, but it measured 83 dBm. This measured 77, and this one 74. So you can tell these look like beams for sure. And this was, yeah, these were the 3 beams recorded. This one is the strongest. And when we accumulate the grids, we obtain this one. And essentially, when we compute the maximum, because we do some clustering as well, essentially we get the beams there in the center. Yeah. And something worthwhile showing is how the positioning accuracy changes for across all the positions. So assuming we perform only one measurement, how does the position, how does the accuracy change if the user is here versus here? And in this case, I'm only using a very low resolution of 2 by 2 meters to make this faster. But everything's going to look much better if you instead put the 1 here. But then it also takes longer. This one is already took 30 seconds. For the paper, we actually put here 1000, which was a much slower resolution simulation. And for the journal, we're going to have this in completely parallelized. So it's going to be roughly 20 times faster. Well, it depends on how many cores you have. But in my case, it's about 20 times faster. So this just executed, and we can plot the position accuracy. Again, very low resolution. You can find the images that we include in the paper, and this one has a better resolution. So essentially, in the line of sight, you can see that you get lower position error, and as you go to non-line of sight and further away from the base station, you get higher error. And these are the 2 positions we considered for our main study here. These 2, one in line of sight, one in non-line of sight. So as you can tell, the one in line of sight for one measurement will have a lower error than the one in non-line of sight. And by the way, these look like this because 77 might be not the maximum, but one point that is slightly shifted from the maximum because we sampled the normal distribution, right? And so we are getting here the edges or sort of the secondary values, while the main beam is actually in this direction, in the middle. We got the secondary values because of the sampling of the distribution. Also, we can plot the received power, which we have here. This is our database. We can plot the received power in band 0, and we compute the maximum across beams. So the maximum received power, which is that plot that I showed you, this one. We can essentially correlate the maximum received power in the position with the localization accuracy with this. And if we make the correlation, let me delete all of these to make it easier to show. We have a few more. Let me delete all of these as well. Yes. So as you can tell from these 2, they are relatively correlated. The correlation is essentially this one, which is -84, which makes a lot of sense. Essentially, the higher your received power, the higher your localization accuracy can be. And this has this high correlation with one beam, but because, by the way, if you have if you are receiving a lot of power, that tells a lot already where you might be in that beam, because you might be exactly in the perfect direction of the beam. There's a high correlation there. And it also makes this method quite predictable in terms of what the accuracy might be, since it relates so well with the received power. Now, let us compute the other two images. So, for the multi-parameter simulations, we started with a given set of parameters of doing one report in one beam, in one band, which is this one. This one has a little error here, it should be 1. And then we varied each parameter individually and then all together. So as you see here, we varied, for example, the number of time samples first. So this one is 112, and this one is 114, where we sampled one beam in one subband 4 times, etc. And the same for this one. This is 1, 2, 1, 1, 4, 1, 1, 6, 1, meaning it's one beam measured in 6 bands, reported once. Then the same for the beams. This is 4 beams reported in one band once. And then we did all of them together. And as you can see here, some parameters impact more than others, particularly the beams impact more, and as expected, if we measure all of them together, we get the best accuracy. So let me show you how to do that in the code. We have this here. Let me put first in line of sight, and maybe I don't know if this is going to be very fast. Let me try. 20 seconds we can wait, and essentially this is going to write the result to the CSV folder. I already have here the 2 results that essentially got our results, because this is random processes, so that way you are able to reproduce exactly the same figures. And this just finished. I'm going to explain in a second how that can work. Essentially, you set here the base parameters, which is the parameters from which we are going to change things. And then here you make a list of lists, while inside each of this one, while each of these lists is the new parameter. So for example, we want here 1 band, and here we want to measure these 2 bands, and these 3 bands, and this is the band index for the measurements. And for the power is quite simple. We simply have to make a list of the number of beams we want. So in this case, it's going to be 1 beam, and then 2 beams, 3, etc. So if we plot that, because the CSV path, we already got it from there. What an interesting output, which I'm going to analyze soon. But essentially this is what we get. And this looks slightly different than a figure, although it's not too different. But essentially, as you increase the number of repetitions and as you change the seed, you'll get different outputs. And some look better than others. But essentially, this is how it looks. And it should be noted that sometimes this is not going to decay perfectly always, because there might be some noises that in introducing a new measurement might make it actually might confuse the model. Essentially, this is not a model, this is quite straightforward, but it might introduce the wrong information. And then in the journal, which we're about to release as well, we already have a method that is much more robust to these things, and it's usually always always decreasing. But for the most part, if you increase the number of repetitions, you'll see the same trends. So this was for the line of sight position. So with one, it started around 20 meters, and that's more or less what we have here, around, yeah. But then it decreased, and that's what we are seeing here too. Now, if we change this to non-line of sight, and we perform the same experiment, this is also, yeah, this is writing to the CSV, and we're going to see a new CSV pop up here once these results finish. Most of these parameters are for visualization purpose. We didn't plot yet. Let me plot it. Yeah. So as you can see, the beams, yeah, essentially it's the same thing. I edited this figure in the sense of putting the label in better places, and then sometimes I had to move a bit the legends just so they were more easier to see. I edited this in SVG with Inkscape, actually, in Linux. But yeah, I think you can see the trend. They are practically the same. And this is how we generated all the figures. And I also saved the figures exactly in this in SVG, and the ones we include in the paper in PDF. I think these are exactly the same ones. Yeah, I think they are. And from these guys, you see here the CSVs. Let me open. Oh, by the way, if you want to generate exactly the same figures as within the paper, you just have to uncomment that. Yeah, and you get exactly the same figures as we got in the paper. This should be exactly the same. Yeah, exactly the same one. I'm gonna fix this error before giving this to you. I don't know what's going on now. And I was gonna show you that if you open one of these CSVs, which I have opened here, perhaps let me, yeah, you can see here the confidence level. This is the position error, the maximum position error of a certain confidence. So for example, this value is, I'm 90% confident that all errors with this measurement characteristic have less than 8 meters of error. And that's how we generated this table here. We know the confidence we want, and we know the error we want, and then we only had to take them from the right places. For example, for 111, for line of sight. Oh, sorry, I opened the non-line of sight. This is the line of sight one. And the line of sight one, we should see a relatively big error there. We want to see the cumulative, not the confidence. This is essentially 99% of the results were under this value. And for 90%, we got around 90%, 40, well, actually right on spot. This one is for, even with 100 samples, we got already very good accuracy sometimes. So yeah, this is how we made the table, just copying values from the right places. And I think now you know how to reproduce all the results. Let me know if you have any questions. You can do that by sending me an email, and my email is in the paper. It's just my first name @asu.edu, and I look forward to see you in the conference and to interact with you in case you need any help here. I would definitely suggest you use the code in the journal instead of this one, which we are about to release. So if you are interested in this work, let me know, and I can perhaps expedite how soon we release the code for the journal, because it's more stable and it has better methods and it has parallelism and it has a few other tools you might like. So yep, thank you for watching, and let me know in case I can help with anything, and all the best and good luck with your research. Thank you.